everyone, and welcome back to lesson 23-2. Today we are going to move into talking about the double angle identities. So on page 309 in your Springboard book, we're starting with number 4 today, and we're looking at the double angle identities. So the reason they have the double angle name is because we're talking about 2 theta, which we know we could officially rewrite as just theta plus theta, right? They're equivalent values. So again, the double angles are the ones where you're going to see the 2 in front of your theta, not a squared, but a 2 times, right? Now, when we're trying to find these, if we verify that these identities hold true, right? We're verifying. So we're going to make sure the left-hand side equals the right-hand side. So again, we know that we can rewrite sine of 2 theta from what we were talking about up above as sine of theta plus theta. Well, this is the sine sum theorem, right? And we know that that would be sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. And in this case, alpha and beta are our theta values, right? So both of these are being replaced with theta. Well, we have one sine cosine and then another officially sine cosine. Again, you can write that order reversed because it's multiplication. So officially we have 2 sine theta cosine theta to show that that worked out. Same thing's going to happen with B and C. We can verify that the left-hand side equals the right-hand side. So again, we can rewrite cosine of 2 theta is theta plus theta. And again, using our sum theorem, we know that this would be cosine of theta times cosine of theta minus sine of theta times sine of theta. Again, just plugging in theta for alpha and beta. Well, we know cosine times cosine is cosine squared theta, and sine times sine is sine squared theta. So again, checks out in our verification. Last but not least, tangent of theta plus theta. We know that we would have a tangent of alpha plus tangent of beta, which again are both tangent of thetas this time for alpha and beta, all divided by 1 minus tan alpha times tan beta, or theta and theta again when we substitute that in this time. Well, again, we can combine the tangent and the tangent to become 2 tangents after we add, and then all divided by 1 minus tangent squared theta, which again checks out to what we wanted it to up above, okay? Now officially, we can actually take the cosine of 2 theta and derive it a little bit further to have some other forms, okay? Because if we take cosine squared and sine squared, we know we can make some substitutions using Pythagorean identities. So cosine of 2 theta actually has a couple other forms because we can write it in terms of cosine only or sine only. So again, originally we derived it to be this cosine squared minus sine squared. But if we want it in terms of cosine only, we can make the substitution here that we would have cosine squared theta minus 1 minus cosine squared theta, which is going to simplify to be cosine squared theta minus 1 plus cosine squared, or 2 cosine squareds when we add them together minus 1. Okay, so this is another version of cosine of 2 theta that we sometimes will use. And we can do the same thing then for sine of 2 theta as well. Cosine of 2 theta, we can also write it in terms of sine only because again, cosine squared minus sine squared. We can make that substitution for cosine squared as 1 minus sine squared. We still have the minus sine squared, so now we have 1 minus 2 sine squared theta is one final way to write cosine of 2 theta. So cosine of 2 theta has a lot of options that we can see here, okay? So that being said, you definitely want to write down your different ways. And again, the double angles, we only have one way to write down sine of 2 theta and tangent of 2 theta. Cosine, however, has a couple different options to write down. So you definitely want to have that list handy. Now, using these values, we can go back to what we talked about with the sum and the difference formulas and use triangles that we draw in to calculate the double angle formulas as well. So if they are asking us to find cosine of theta, sine of 2 theta, and cosine of 2 theta, what we would do is, again, draw in our triangles. In this case, we have a positive sine value that's between pi over 2 and pi, aka quadrant 2. They're giving us the opposite over the hypotenuse, and then we can use Pythagorean theorem to find our missing side, which is going to actually be negative because, again, it's quadrant 2. So cosine is going to be negative square root of 15 over the hypotenuse of 4. And then we can use, for sine of 2 theta, the sine that we were given and the cosine that we were just found to plug into that formula of 2 times sine theta times cosine theta to get our double angle for sine. And then cosine, you have a couple different options. This one, they chose to use the cosine squared minus sine squared since we had both of them, and then simplify that to get our final fractional value there. Okay, so we have a couple different examples to go through then on page 310. With part A. And again, they're not giving you a ton of room. So you're going to either want to write in the My Notes section or very, very tiny. So the first thing they're telling us is that we have theta between 0 and pi over 2. So that's a quadrant 1 value, right? If you're starting at 0, angles ending at pi over 2. So here's our theta. And since they're giving us cosine, we know that's the adjacent side over the hypotenuse. And this is going to end up being a 3, 4, 5 right triangle. Okay. So from here, we are able to calculate a couple different things. Sine of theta is going to be the opposite over the hypotenuse. And then tangent of theta is the opposite over the adjacent. Now, using that information, we can now find sine of 2 theta and tangent of 2 theta. Because we know sine of 2 theta is equal to the 2 times the sine of theta times the cosine of theta. So we can use those fractional values to plug in. So sine of theta, again, we found to be 4 over 5. Cosine of theta was given to us as 3 over 5. And when we simplify this, 2 times 4 times 3 is 24. 5 times 5 is 25. So there's our simplified value as much as possible. And then tangent of 2 theta, we know is 2 times the tangent of theta over 1 minus the tangent squared of theta. And for this one, we know that our tangent is 4/3. So we're going to multiply that by 2. And then in the denominator, 1 minus 4/3 squared. Our answer there. Now, for those of you with a slightly older calculator, a reminder, I would do this as 2 steps so you don't have to worry about the fraction within the fraction. So 2 times 4/3 is going to be 8/3. And then divided by our other fractional value of 1 minus 4/3 is going to be negative 7/9. And then finally, we can take 8/3 divided by 7/9. And then to get our rational answer of 24/7. Oops, I forgot the negative in here. So that should be a negative value as well. Negative 7 over 9. Or negative 24 over 7. Now, sometimes we're going to deal with some that are not quite so pretty, with like part B, where we have some fractional values involved, or excuse me, radical values involved. So notice here, they're telling us that this is in quadrant 4, right? We have 3 pi over 2 to 2 pi. So we know that theta this time is in quadrant 4. And they're telling us the tangent, our opposite over our adjacent, is 8 over 17, with 8 needing to be the negated value since it's in quadrant 4, we went down. So a couple of things here. We want cosine of theta, cosine of 2 theta, and tangent of 2 theta. Well, cosine of theta is going to be our adjacent over our hypotenuse. So this time our hypotenuse is going to be the square root of 17 squared plus 8 squared, which 17 squared plus 8 squared is a pretty large number. 317 squared plus 8 squared. 353, which is not a perfect square and actually has no perfect squares that go into it. So C is going to be the square root of 353. So again, kind of an ugly hypotenuse value here, which means our cosine is 17 divided by that. Or if you rationalize 17 square root of 353 over 353. Now, if we're looking for the cosine of 2 theta, you have some options with your formulas, right? This time I would recommend using 1 minus 2 cosine squared theta, or excuse me, 2 cosine squared theta minus 1. And the reason being, we have the cosine on this one, right? We have the cosine, we just found it. So instead of working to have to find the sine as well, since they didn't give that to us, if we use 2 cosine squared theta minus 1, we can get our answer a little bit quicker than having to also find the sine in this one. So 17 over the square root of 353 squared minus 1. Well, the nice thing here is when we square a square root, it hopefully is going, it usually always goes away, right? We're going to square this 353 squared and then minus 1. You get a fractional value, but it's again a little bit nicer than what we would have had before. So 225 over 353. Now, in my notes, personally, I actually did find the sine and used 1 minus 2 sine squared, and I got the same answer. So it just shows you can use any of the 3 for the cosine of 2 theta and get the same answer. Finally, we have tangent of 2 theta to look for. And a reminder with tangent of 2 theta, that is 2 tan theta over 1 minus tangent squared theta. And they gave us the tangent, so that makes our lives a lot easier, right? We're just going to plug in negative 8 over 17. And again, very carefully type this into our calculator. Again, I highly recommend just doing it as 2 separate fractions, especially if you don't have pretty print. So 2 times negative 8 over 17. We get negative 1617. And then in our denominator, there we go. We get 225 over 289. So finally, we can take the negative 16 over 17 and to minimize my risk, I'm just going to hit second answer to get that fraction back in there, divide by that. And we finally get the final answer of negative 272 over 225. All right, so we will definitely be working more with this in class, but again, make sure you have this piece written down. You want these double angle identities ready to go, and we will work more with them in class. Thanks, everyone.